Welcome back. So we are class 13. This is the last class. We're essentially looking today at multiple imputation as our last topic. This is really a great topic. It's essentially, to be honest, I think it's still underutilized to some extent. I think it's a wonderful tool essentially to confirm insights into associations. And the interesting thing is that with multiple imputation, you can essentially reduce the effect that missing values have on your research insights and your research results. So when we look, okay, so before we start that, let me actually go back. I'm gonna first have a quick look at the syllabus. So again, today we're talking about missing data as a concept and how to handle them. We're looking at data mechanisms, missing data mechanisms for multiple imputation, and we will look into how to potentially deal with missing data. We will do that with the so-called chain data that essentially investigates the effect on log transform viral load in CD4 cells with or without HART. It's a highly active retroviral therapy. This is a package contained in R. Q&A on homework 2. Well, you didn't really loop back many questions. I hope if there are questions, then there will be a discussion about entries and questions to me or to your fellow colleagues. Of note also that for today's lab, no submission is required. So this will not be required to be submitted. Homework 2 is due on Thursday. Apologies again for posting it somewhat too late. That's why you get a couple of extra days. There's also the Perkins data that essentially allows for you to review missing data and approaches to that. Of note is just that next week on Sunday, I will be posting exam 2, which is an online timed exam, just in the same fashion as exam 1. And of note, please, 12/13 is the end of the semester and research note 2 is due. So I hope by now you have all seen the grades of research note 1. Please look back to me if any questions concerning my comments, concerning my feedback. Overall, it was very good work. Some minor details are to be discussed, and I've mentioned them in the comments. So first of all, when you submit, and you submit multiple times, so I allow for multiple attempts, and please make sure that when you submit a new version, you need to submit all the files, also from the previous attempts, because otherwise I'm facing several iterations and I really just want to look at the last submitted attempt. So please include all files in your final submission and don't expect me to go through all attempts that have been occurring before. I will definitely only grade the last attempt. So I made an exception for the last, for the first research note, but moving forward, I don't have the bandwidth to look through all attempts, and please understand and support me on that. Furthermore, it also makes my life more easier when you include your name in the file name. Also makes it a mistaken, and avoids mistakes, and essentially allows for me to identify the file name without any ambiguity and potential errors. Good. So this was this. These are the more administrative aspects of it. Okay, so this was to look at the syllabus, and now we're gonna go into class 1. We are essentially now getting started. So this is the last class, class 13. So we're looking at the chain data in a confounding model. We're looking at concepts of handling of missing data. We'll discuss what missing data is and why it's missing. We're looking at the mechanisms for missing data, how missing data can be approached. We'll be talking about ad hoc approaches of missing data and associated issues, and we'll be discussing multiple imputation as a method to counteract to missing data in your data set. The lab will contain missing data handling using the mice package. And this is essentially what we will be doing in class, which is we're going step by step through it and we look at things a little bit more detail. So Q&A from homework 2. This we need to research. So these are the slides from Professor Sang, and we are not having an online class. So from there on, the Q&A is restricted to the discussion board. Good. So the chain data. So the chain data is a subset of the Community Health Advisory and Information Network study, the chain study. It's a longitudinal cohort study of HIV-infected individuals in New York City, conducted by Columbia University, and recruited in 1994 from large populations, large number of HIV patients from medical and social service agencies in New York. They were interviewed up to 8 times, and 532 chain participants completed at least one interview, either first, second, or third round of interview. We are discussing, we are discarding the longitudinal aspect of the data for the very reason that it becoming just too complex, and it adds an additional layer of complication to it. So we are basically getting started now by essentially looking now at our data. So we are again opening the data with the Haven package. We're loading it with the read SPSS function. We see here we have 532 entries. We have 8 variables. This is 6 by 8 as here showed with the head function. The variables we have is the log virus load. So the viral load is essentially a reflection of the activity of the virus in the body. Age is the age of the patient. Income is the annual family income. Health is continuous physical health. That's usually a self-reported marker that I don't know what, I did not read the study design of the chain study. No apologies for that, but I assume it's something like the short form 36 that essentially allows to quantify physical health using general questions that provide insight into the self-reported physical health of the patient. Mental is a binary measure of poor mental health. Not sure, but this is coming from possibly also from the SF36 that has a physical health component and mental health component. But I don't know, it's coded as a binary measure. So this is for now for this example that we need to know. Damage is an interval for the CD4 count, which is an indicator of how much damage HIV has caused at this point in time. Damage here means, so the virus essentially gets into CD4 T lymphocytes and will there essentially reduce the number of circulating T lymphocytes, which is also the cause for the immunodeficiency. And so a diminished CD4 count essentially is a reflection of a progressed HIV that essentially is to some extent quite active in the patient. As opposed to the viral load, this is essentially the activity to that extent, which has not yet resulted in a substantial lowering of the CD4 count. However, both in conjunction are markers of the activity of the level, and this is essentially what you will find in most medical reports pertaining HIV. Treatment is now a 3-level ordered variable. So treatment, as most of you likely know, treatment for HIV is a highly active antiretroviral therapy, the so-called HART regimen, which are, I believe, 3 or 4 different medications that do modulate the immune system. So we have 3 levels. We have 0 is not currently taking HART, 1 taking HART, but are not adherent, non-adherent to the regimen, and 2 taking HART and are adherent to the regimen. So the idea essentially for this modeling purpose that we're using today as our example is that we want to assess the treatment's impact on the viral load. Viral load as a marker of the activity of the virus in the body. So the HART regimen is meant to modulate the viral load and to remove as an antiretroviral drug, essentially to reduce the number of replications of the virus and the viral load. So the outcome here, Y, is essentially our viral load, whereas our S is going to be treatment. In a univariate model, this essentially is our intercept. This is again coefficient and treatment, yes, no, or 0, 1, and 2. This is our residual error. And in the multivariate model, we additionally adjusting for confounders, which is essentially age, income, healthy, and mental. So damage was excluded here from this multivariate model, mainly because of missing data. And secondly, because of the intercorrelation between the outcome. So when we are now comparing the univariate to the multivariate model, we see essentially, we see an intercept, we see a comparable, so we see a decrease in the viral load, the log transformed viral load, which is consistent with what the HART regimen essentially should induce. Of note, this is consistent with the multivariate model that is additionally adjusted for these 4 confounding factors. And what is interesting to see is that the intercept increases, but the slope of the respective treatment regimen is consistent. So what's interesting here to see is that the observations differ. So now you can ask yourself the question, like, why is that? So the reason for that is that under default conditions, R will only use complete cases, meaning as soon as you have one missing variable in any one missing data entry in one of the variables, the entire data row will be excluded, meaning that here 353 observations were used to essentially analyze the effect of the treatment on the viral load. So now when including additional variables, you also increase the probability that you have missing values, and indeed they're missing values. So for that very reason, these cases entirely drop out, and this reduced our observation count, or sample size, from 353 down to 344. And you will see that with all models that you essentially do. So always make sure that you compare the observation count, and it has different labels in different models, but usually it's groups or IDs or cases. So whatever it is, always compare it with inclusion of every variable, because your degrees of freedom and your sample size will be changed because missing values. And you need to be aware of that. Whenever you do analysis, you always got to be aware of missing values. So now, to quantify the pattern and to inspect the pattern of missing data, you essentially have here a very elegant function that will allow you, so from the mice package, that will allow you to essentially investigate the pattern that you have within your data. So when you look here, let's look at the characterization. So we have here on the right side, we have the number of missing entries. So if all variables are there, there's 0 missing data. If there's 1 missing, you have 1 missing data. And if all are missing, you have 7 missing data, so 7 zeros. Now, what is not depicted is that all are missing, so this would be in totally an arrow, and this would be here an additional entry, which would imply that there's essentially ID missing, and then this would be an inexistent patient. So this will always be complete. So the ID row will never be missing because that defines the entry and that entry for that individual. So now we have 335 entries with no missing data. So then we have 122 with only one data, which is the log virus. So we have 9 with missing damage, with 28 with 2 missing data points. And so essentially you can complete the count down to essentially completing your data set and your inspection. So by that, you know which data essentially is missing and what the pattern of this missingness are. So the first column provides the frequency, last column, the number of missing entries, and the bottom row provides the number of missing entries per variable. So generally it can be said that missing data refers to data values that were intended to be collected, but were not available for some reason. So essentially, 3 broad categories of reasons are to be considered. One is that characteristic of the study participants led to the data row not being collected. So participants did not answer the surveys, participants did not show up to the assessment, etc., etc. Characteristics of study design could be that the study required too much time, which is too involved for the patient, and the patient opted out to participate. And the last and probably also the most tricky one is an interaction between both, which basically where the sickest patients were not able to participate and were not able to complete their data collection visit, and were not able to provide sufficient data for their data entry. So it's really characteristic of the study participant, characteristic of study design, and the interaction between design and participant demographics and characteristics. So Little and Rubin defined missingness as follows. So it can be missing completely at random, where a variable is missing completely at random if the probability of missingness is the same for all respondents. What does that mean? That means that the missing data is basically just a random subset and not differing from the overall population, neither from the population of those that did have complete data. So that means that there's the total generalizability, and as such, this missing data subset, this subset with missing data, can be entirely ignored to some extent because it will not bias the results. So that would also imply that the probability of missingness does not relate to subject characteristic, neither to design or participant, and it does not depend on any observable or unobservable data, meaning we will not see in the data a difference between the sample with missing data and the sample with complete data, and there will also not be any unobserved differences. So as you can imagine, this is virtually impossible to 100% ascertain, and for that very reason, some form of systematic missingness is to be expected. However, what are examples of such missing completely at random cases? There could be an accidental loss of a subset of study records. But even then, it's like, so somebody puts all the files in a box and drives the box home, and this car gets stolen on the way, and this box never returns. Even there, you have some form of systematic bias because it may come from one site, it may come from one consortium. So you don't know what unobserved factors could have led to this missing completely at random or missing at random in that regard. So there are always some form of problems that could be with missing data. Then it could be that an air pollution study parents are relocating. Again, here you potentially also have unobserved factors, but it's for the sake of this class and for the sake of the example, I think this is considerable missing completely at random. So it's MCAR. Missing by design is the last listed example here. That could be for example, that assignments to groups is random, and then these groups are to answer different sets of questions, and then the groups per se may have dropped out. So from that end, you're trying to kind of make it easier to overcome. You need to keep in mind when doing that, you get missing data by design, so you have this rotating kind of setting. But nevertheless, when knowing why you have missing data, you essentially, it's easier to counteract this missing data. So knowledge is power, and then once you actually know why this data is missing, makes it easier for you to find ways to work around that. So I'm not a survey expert. I have never conducted such missing by design, but I think this is which you should be very simply able to simply counteract. In MCAR, throwing out cases of missing data will not cause any differences in the inferences. So it will only cause a loss of statistical power because of reduced sample size, but it will not cause a bias, which you're afraid of, because as soon as you have biased subpopulations with missing data as compared to those that have complete data, then you're not looking at the MCAR anymore. So in the perfect setting for MCAR, you will exclude an entire case without creating any bias. So it is to some extent possible to test with the available data, but in many cases it's not MCAR. So a slightly less random kind of missingness is missing at random. So we can quantify it. We can quantify randomness based only on available information. And we have data of that available for every observed subject, and we can quantify it. At this point, we can essentially restrict the missingness, the reasons for missingness to the subject characteristics, and we have them available at the time of analysis, which kind of puts us at advantage because we understand the missingness and we know what missingness was caused. Then it would be non-missing. But since we have now data that essentially confirms this as being random based on the available data, we can quantify that it was random based on the data at hand. But we do not, by design, we do not have any form of evidence that we have completely at random missingness at hand. So examples, and that's a frequent example that we actually see in our populations and our studies, which is important to test for. So doctors are less likely to order blood tests in a study for patients who are sicker. It's usually in many cases, I would rather say in observational data, it's the other way around, because you will see patients that are about to get hospitalized or who are based on their clinical characteristics and then their clinical profile are actually sicker, are actually more likely to receive more blood tests, more assessment, and higher frequency visits. So it can go in both directions. So what's important to understand is that you see dynamics that are basically explained by what you are. So you see dynamics in your data that is explained by the characteristics that you've seen. So you gain insight in what's happening. So then you have the next study, data missingness issue is when patients or subjects that are sicker dropping out of a study or have stronger side effects from the intervention. So this is actually a problem that basically leads to some form of selection bias in randomized controlled trial, and is actually important to keep in mind, because you're testing blood pressure medication and the patient has repeated hypertension, and he repeatedly faints or has like side effects to the blood pressure medication and this low blood pressure. This individual either has to be dropped or will voluntarily drop. So, so this goes then hand in hand with either he or she drops because he or she doesn't want to participate anymore, or secondly, the protocol requires that the subject is removed because there's some safety guard in place that basically will drop the patient as soon as his blood pressures for a persistent period of a longer contracted period of time below a certain threshold. And so missing not at random is an observation that is not missing at random if the missingness depends on unobserved characteristics like the value of observation itself. Depends on unobserved characteristics like the value of the observation itself. So if you have an observation and it would, for example, mean, and the example here is good, that wealthy people are less likely to report their income. Outcome variables are measures of quality of life, and the subject failed to complete the instrument or questionnaire on occasions when their quality of life is compromised. So the quality of life basically renders the patients less likely to fill out the quality of life survey. And parents of children who are obese are either less or more likely to sign the consent form than parents of children that are not obese for participation in a weight loss study or for visit concerning weight loss. So these are examples which essentially are not at random, where basically the value of your outcome or your outcome variable essentially is informing or is leading to missing values. So that would be considered not at random. If it's not at random, it must be explicitly modeled, or else you must accept the bias and influences. And that is tricky, obviously, as you can see. So it's really complicated to distinguish between missing at random and missing not at random, because hypothetically you want missing completely at random that basically does not create biases. And it's virtually impossible to know if this is really missing at random or missing not at random. And to some extent, you would like to understand the difference, but it won't be possible. You only have this data at hand, and only the available data will allow you to gain some insights into the causes of missingness and whether there's a cause for missingness. And this is unfortunately not insightful enough. So when thinking about missing data, so essentially you have simple fixes. So you essentially have a complete case analysis and complete variable analysis. So you basically complete case analysis would be analysis on cases with complete data or variables. At the very best, it's very inefficient because it reduces your sample size. It may potentially bias your result, and it's considered to be resting on a missing completely at random assumption. And you think that this is a random sample of the complete sample, which is unfortunately not true in many cases. So the complete variable analysis, and this is what I really would suggest to everybody. So when dropping cases, when including variables, always go down. So there, I understand that there are models that essentially allow for you to And there are functions that basically allow for you to stepwise exclude model variables based on their predictive accuracy. And one of the problems is that this does to some extent contain the information of sample size, but I think it's super important that you understand with which step of your model selection you are losing how many cases. So I think it always makes sense that you're not going from a univariate model right away to a multivariate model with 10 different variables, even if the stepwise logistic regression or whatever approach you use tells you, okay, so that is your model. I think it makes sense to always understand how many subjects, how many cases did you lose with each step, and then make a decision on whether you want to include this variable or not, and not just base it purely on internal algorithms. But that's my personal take on that. So I think this is important to always understand missing values, characteristics, and also the ranges that are included in each analysis. So for a complete variable analysis, you only use variables with complete data on all cases. Of course, the problem is that, well, you would retain the full sample size in a perfect case scenario. But obviously, if you need to control or want to control or think these are relevant based on your hypothesis and your underlying research question, you will not be able to only resort to variables with complete data. So this is a problematic approach. Both approaches essentially can preclude subgroup analysis because data reduction may be the case for data or variable reduction may be the case for both. So these subgroup analyses are going to be quite complicated in this context. So there are some simple approaches how to essentially get around it. So there is one that Professor Zhang shows here, which is the imputation by filling with the mean. So basically you take a mean value for the data point and you essentially use this to impute the missing entries. If you have longitudinal data, and this comes now from my world, if you have longitudinal data, you can also use patient-specific mean, or you can also, we do that quite frequently in our longitudinal analysis, you carry the last value forward, and you have a certain range up until you are carrying forward, or otherwise you're moving backwards and you take the following levels. And there are various different approaches. It really depends very much on the data. It depends on the granularity of your data, and it depends to what extent how you want to approach it. Also on the analytical methods that you want to apply later on. So when you essentially are including now mean imputations and use this to kind of complete your missing data, the scenario you get essentially, and this is, you still have, you have here 0, you have here subfraction with 0, which would be something I would already investigate here because it depends what this value would be. Usually a 0 value is always to some extent kind of alerting, and I would always investigate the 0 value. It depends on the variable, obviously. So there are cases where there exist 0 variables, but I would always investigate them and make sure you're really seeing what you're seeing. So lab parameter, for example, clinical parameter are very seldom 0. Just keep that in mind for an analysis you're gonna look at later on. So now you get here this scatter of W as a function of Y. You have here this 0 value of W, and here it's a nice distribution. And now here, for the second one with the mean imputed data, so here the correlation is 0.92. And this is already also alerting with the 0 values, because this obviously this will very much destroy your correlation. And it's not really sure, depending on the variable, it's really questionable why it's 0. So we'll definitely look at this. So now when we mean impute the data, we're decreasing our correlation coefficient, because remember, correlation basically tests some null hypothesis that the slope of this association between x and y is essentially different, significantly different from a flat line. So obviously, if you're including now a mean as one constant value, that basically will result now in one flat line, this is not going to help your correlation coefficient. So this is to be kept in mind when doing mean imputed W's and Y's. A better approach is essentially where you use imputation by regression. And it's pretty straightforward what you're doing, right? It makes a lot of sense. So you take all your complete data sets, you fit a regression line, and you predict each value on the x-axis that is missing. So if you have patient X, Y, Z, you know it's X, but you don't know the Y, you basically model it using the predict function, or you model it using the equation. So that's fairly easy. This essentially will increase your correlation coefficient. So you also see a smaller mean squared error, which is essentially a marker of this accuracy of this prediction equation. Essentially, it's a mark of it's a combined mark of accuracy and precision for use in predictive accuracies. Another way to do that is multiple imputation. So multiple imputation procedures and rationales are essentially our attempts to take into account the sampling variability and the model uncertainty. So it uses the available data to create several complete data sets. And these will be sampled somewhat. So it samples these data sets, right? So it randomly samples these data sets, and these data analyses are then performed on each of the imputed data sets. So the results from each data sets are then combined using standard rules. So you pool the results, and by that essentially you get a very solid and very accurate model containing all variables as a complete variable. You do this with I think the most common approach is Monte Carlo simulation, where you basically iteratively repeat the procedure to an extent, creating new data sets with each iteration. And this essentially will allow for an accurate prediction of the estimate. So you examine missing data among variables of interest. So you did exploratory data analysis, and you find out the missing data patterns, just like we did before. You identify auxiliary variables as needed, which you may need for creating that model. Then you impute. So you specify models for the relevant variables. You use those models to predict these missing values, and you repeat it for m times to create m complete data sets. So you do this random sampling repeatedly, and you get repeatedly data sets with all complete data, with no missing data, in your sub data set. Then you perform your desired analysis for each data set, and then in the pooling step, you combine the estimates across data sets using common rules of pooling. And we will talk about these rules in a second. So an analyst must have to specify a model for the data. These vary across software packages. So there's the mice package, which is a considerably easy conditional model method to essentially build multiple models that allow for you to fill the missing data and to get over the limitation of the missing data, and by that preserving your full analytical power. So these conditional models you will adapt concerning the variable you actually analyze. So you can have a fully conditional specification method, which basically uses all models and all interactions in your data, all your associations. Then you have it does not assume a joint distribution and allows the use of separate different distribution across variables. And you will utilize Markov chain Monte Carlo simulations to essentially get these multiple data sets and analyses, which you will then use to pool. So now let's go back to our model, the chain analysis. So we basically obtain estimates for each beta head for each of the M data sets, as well as the standard errors. So to obtain now an overall point estimate, we average over the estimates from the separate imputed data sets. So the variance estimate reflects the variation within and between imputation. So basically it takes a standard error of that beta is essentially a variance within each imputation, and you divide it by 1 plus 1 divided by the number of imputations of the number of your data sets, multiplied by the variance between and the correction factor, where VW is 1 divided by M, and this is where M equals 1 to the maximum number of imputation, standard deviation variance, and that's the variance within the sample. So this is a pooled variance, and the variance between. So it's the sum. So this is essentially a pooled variance that is being built. So you have from M equals 1 to M. For each M, you get 1 variance. So you get variance, let's say that factors for our example would be 50. So you have from 1 to 50, you have 50 variances. And then you basically divide these 50 variances by M. And by that, you get an average pooled variance. All right, this is basically, it's the same. All of you must have must remember from the introductory courses class that for the independent sample t-test, for example, you will need to quantify a pooled variance to essentially get to a standard deviation of the difference that will, a standard error of the difference that essentially allows you to get to your t-score in the t-distribution. So this is essentially the same that you're doing here. You're creating a pooled variance between all imputed data sets. And then you have a variance between, where you basically have 1 divided by the degrees of freedom. And you have the variance between is the beta M minus the beta head M for each of these estimates minus the beta head overall. And this essentially is to be compared with the ANOVA, where you almost like you have a variance between, where you have the grand mean, and you calculate the difference of each groups in your ANOVA to that grand mean. It goes in the same direction. So in terms of thinking, think again kind of along these lines. So the correction factor is then here, the variance between divided by the number of imputations. So if this is being calculated as the variability of each beta estimate over this overall estimated pooled beta head, this will essentially be this variance between divided by the number of imputations. These are the rules that are being employed for the pooling of your imputations. So these rules work then for any parameter of interest. So now we're here essentially looking at the chain data. This is again, this is just like we said here, this is a fully conditional specification method that does not assume joint distribution and allows this different distribution across variables. So the mice package will essentially, oh, I didn't manage that, sorry for that. I didn't know I could do that. Okay, sorry. So we will essentially impute now the data. We will create 50 copies. So that's 50 imputations. So we're creating data mice from our chain package. So we say function mice. We're using chain. We're doing 50 imputations, so 50 copies, 50 datasets, imputed datasets. The methods we're using is now basically individualized for each variable we're looking at. So we have for ID, it's a complete set, like what you're gonna do with ID. How could you deal with that? There will be no missing value, and also it's non-logical to kind of impute that. Then we have PMM. This is now log virus. And this is a question I'm actually kind of interested in. That's something I'm actually going to ask Professor Singh, because I really want to know myself. When you have log virus, so this is log transformed parameter, right? If you hypothetically have the original virus load not log transformed, it would be interesting to play that through and to really simulate that through. And what my theory holds, I would think that if you are imputing log virus here with, okay, so you have three methods. Okay, let's back that, like come back to that. So we have PMM as an imputation method. We have logreg as an imputation measurement. We have ordinal logistic regression, polynomial ordinal logistic regression method. So we have here, we do nothing for ID. We do predicted mean matching for log virus, so for age, so for income, so for healthy, which are all continuous variables. So now when we come to the binary parameter, so that's health, that was mental. Mental was 0 and 1. So here we do a logistic regression. And then we have the polytomous ordinal logistic regression we're doing for damage. That was from 1 to 7, I believe, on the scale. And for treatment, which is 0, 1, and 2. Print flag means here that we're not looking at what essentially that algorithm is doing. And this is just for the lecture in the lab. We're going to do this, and we look at this now. So now also we included damage in the imputation, and we're going to fill, I think it was quite a large number of missings that were included in the first model. Excluded, not included. Okay, so what I meant to say is, so now we are imputing log virus with a predicted mean matching method. And I was wondering, in case, and this is an interesting use case and an interesting thought, in case you do have the original data that is not log transformed, whether your accuracy doing the imputation in a preceding step before you log transform would improve the accuracy of your model. And I would think it does, because once you have log transformed something, it doesn't follow the common rules with the estimation of normal distribution. So it would be interesting to see whether this would be something one could actually do, and wonder if this would actually be preferable. Very interesting stuff. Just a thought on the side. Okay. So now you examine the imputed data using the summary, and we will see this also in this we will also see this now in this website that is basically it's not really a manual, but it's kind of a walkthrough. So I've shown some of those walkthrough earlier, and Marcel and Bino and Professor Sang have kept those again. So here you can investigate and play around with your mice package. And there are really great things that you can do. So you can plot various patterns, you can look at missing data, you can plot your missing data, and you can really investigate what your data looks like, what it looks like after imputation. So here you're pooling, and we will pool in a second. Here you get pooled variables. We can do that in a second. So this is just very nice documentation that basically should be helpful to understand things in more detail. So now when we go in medias res and we essentially are modeling now our mice fit object, our regression model. So we're basically building linear regression with log variables as being the dependent variable, independent variable, factor treatment, age, income, health, mental, no damage. So we get result of result is pool mice dot fit. And by that, we essentially get, and here's the comparison to the previous model. So we're comparing the one versus another. Damage was only included to essentially factor it into the imputation and into the model that led to this estimate in the computed data set. So but for the direct comparison, you always need the same variables. So essentially you get fairly comparable estimates for each variable. So you get for treatment, you get like, it's slightly lower, but it's kind of point on for the factor. And this is really dependent on to what extent you essentially, you get missing values and to what extent the missing values actually were more prevalent in a certain condition. So logic here would dictate for me personally that when you have here an estimate for factor treatment one were those that were non-adherent, and I would conclude that there is a greater difference between your estimate and your indeed found value because you just have more missing values. Somebody who's not adherent with this hard regimen is also going to be less likely to be adherent in other ways and may not have filled out the surveys or may not, I don't know, or may not have showed up, but you have less entries for each individual. Something along these lines, I would assume, could be one of the possibility. But this is speculating. So it's sometimes looking at these model summaries is essentially hypothesis generating. So essentially you see something and then you need to dig deeper into what causes your observation. So if I see here differences, so this is a difference between factor treatment 1 is 0.2, whereas the difference for factor treatment 1 is 0.2, factor treatment 2 is only 0.01, less even 0.007. So this is actually a really small number, right? So I would argue that this difference in difference is essentially something worthwhile to look at, but there's more missing values. So find some other explanation whether it could be the case. But this is just essentially speculating. So, but you see, it's fairly point on. You get standard errors that are kind of comparable, and overall the multiple imputation did nicely corroborate and confirm the insights from the initial model. So you can make a couple of points about the strength of multiple imputation, mainly in the realm of sample size, obviously. So it will maintain an entire data set and use all available information, which of course makes it strong. And you basically have more statistical power, you have more analytical power, you will get a more accurate estimate. However, some assumptions are made in the realm of multiple imputation. So a bias, for example, could be there and you wouldn't even know, because your weak assumptions that you have actually made about the missing data mechanisms is not really necessarily correct, right? So sampling and modeling does properly reflect the two kinds of uncertainty. So essentially you have a sampling uncertainty and you have a model uncertainty. So there's a lot of potential inaccuracies that are basically meshed into this. An advantage is that the relationships between the variables are maintained, because the estimate that you use to fill your missing value essentially is a resultant of all these variables, the relationship between all these variables. And you can essentially use one set of these imputed data sets. You can repeatedly use that. So if you compute this once, you create a new collection of data sets, which essentially you can use for any analyses that you want to conduct, right? So it doesn't mean that this is one specific analysis that has to be done on this data set, so you can use this for various other purposes. So you're creating such an imputed data set, and you can work with that until your analyses are all completed, and it will be consistent with the same combination of data sets, multiply imputed data sets. Multiply. Weakness is obviously the complexity to some extent, which is with current software is not really a problem anymore. In addition to that, the complexity is also, you need to make sure that you understand how you did the multiple imputation. You need to know how to explain it to reviewers and editors. And it's sometimes interpretation should be a solid, accurate estimate. And then it really comes down to how you are presenting it in your data, whether it's a sensitivity analysis or whether it's a main analysis. So it's really, it's a considerably accepted method. So multiple imputation is definitely something which has found its way in like mainstream analysis, even in the medical world and in my world, which is a subset of the medical world and the nephrology world. Multiple imputation on epidemiological studies is found quite frequently. Further, you have to rely on modeling assumptions, and this is basically something you cannot ignore. The imputation model should be congenial or consistent with the analytical model, so it should be the same model that you essentially can compare it. It also needs to include transformations to variables in the analytical model. So the only question is what I mentioned before, whether you want to do it before and after. And so I'll investigate that in case I find something out. I'm gonna let you know if there's something behind what I just mentioned. So all relationships between variables should be represented and estimated simultaneously. Otherwise, you're imputing values assuming they're uncorrelated to the variables that you did not include. So if you are estimating your imputed values, you essentially do have to include all variables that you have at your hand. Sensitivity analyses are important, both within the method and across other methods. So you would use approaches like inverse probability weighting to confirm your insights and your estimates from your main model. Yeah, and today for the lab, we will repeat that multiple imputation-based analysis. And so here the wrong dates, as I forgot those. Tasks for today's labs, Q&A on the homework. So this is for discussion board. And yes, these reminders are obviously obsolete. Please don't forget exam 2 next week. It will be first on Sunday. It's again available for a week. Do it within the course of the week. And don't forget the due date of research note number 2, which is on 12/13, which is Sunday night. All right, good. So that was today's lecture. And I conclude for the theoretical part. We'll be back with the lab. Bye-bye.